Hey, good morning.
Good morning.
Today we will finish designing of frame. Next week we will start to design connections. Once we are done with connection, we will go through new software called RISA connection, how to design your connection using RISA, and then we will start with our project. But before project, we will do second exam first, and then start our project. We started how to calculate different type of load on frame, dead load, live load, and we learned our dead load or live load or wind load will be distributed load over frame, not concentrated load at each joint of Berlin connection. But for dead load and live load, your load will be horizontal projection on the girder of the frame, and your wind load will be distributed load perpendicular to each part of your frame. All parts of frame you have constant uniform distributed load, except the front face maybe depend on what is your height. You can have one value or two value or three value based on your height. We need only to multiply your wind pressure by S, spacing between each main system for frame. And we learned also how to define horizontal projection, how to define perpendicular load on inclined member, how to define all of this type of load using RISA. Finally, your member in frame will have normal, which called B ultimate, will have moment, which called M ultimate, and V ultimate. Anybody here remember how to design member under the effect of shear? Yeah. Do you remember we have phi V 0.6 F yield time what? Area width. Your design shear strength. If your column, you assumed W 16 times 30, for example, and you need to check this cross section is sufficient for this shear or not. Only one step. What is the value of your shear, maximum value of your shear here? 0.18. Your value here. Kept. So V ultimate after combination, remember, all of these diagrams coming from what? Maximum combination. You did your combination, maybe 1.4 dead load, 1.2 dead load, plus 1.6 live load. We have different combinations. So the maximum one. So here is your maximum value of shear on this column. And you can figure out what is the area web for this cross section. One more time, area web for wide flange, this area. Which means the total depth, which is 16 all the time what? T web. All of these properties you can get it from table of wide shape. Once you get your area web multiplied by F yield 0.6 phi V, you can take this one by one. Then you can get your design shear strength. What's your design philosophy for concrete, for steel, for anything? Your V ultimate must be smaller than or equal your design shear strength. That's right? Okay, shear is alone. So I talked about shear specifically. But if you have the same column under the effect of normal, which is compression, and moment, both of them must be considered together. your normal and your moment, both of them together must be added. So how to check your column under the effect of axial compression and bending moment. For shear, it's alone. The internal forces of shear is alone. Anyway. Okay, so we analyze frame using reason and we got the internal forces. Just a quick review. If you have tension member, we have two situations situations we need to design according to. The first one, to prevent yielding. So your ultimate or factor load, tensile load, must be smaller than or equal this term using area gross. If you were to avoid fracture, then your ultimate or factor load from structural analysis must be smaller than or equal this term using area effective. And we learned what is the relationship between area gross and the area effective and how to calculate area effective. If your member under compression means member in truss or column. Column is a member under compression. So your design compressive strength equal phi C time F critical area gross. Anybody remember what is the value of phi C? 0.9? 0.9, I think. F critical. Do you remember how can you get F critical?
Table.
Yes, I'm not sure. During the exam, few students did not use table, use the equation. That's fine, correct. But why? You can get this value from a table in a second using K L over R. Your column may be pin, may be fixed, may be fixed, pin may be fixed, free. Then you can decide what is the value of K. 1, K equal 0.5, equal 0.7, equal 2. L, the total length of your column. R, go ahead to your table. For section properties of your cross section, you can decide which R, Rx or Ry, the minimum value, the smallest value, radius of gyration. Once you get KL over R, go ahead to your table to figure out what is the value of F critical. Using area gross of your cross section and phi, you can figure out what is your design compressive strength for your column or your member, and your internal forces from structural analysis must be smaller than or equal. We learned how to design beam under the effect of bending. Yeah, we have two situations, actually three, but we focused only on two. If your unsupported length of the compression flange smaller than LP, that means we have no concern about lateral torsion buckling. So directly, your design bending moment equal phi, I think 0.9, F yield ZX from table also. But if your unsupported length in between LP and LR, LP and LR depend on table and cross section. You have to use this equation to get your design bending moment. Any question? We learned everything alone. If you have tension member alone, what will happen? If you have compression member alone, what will happen? I'm sorry, not compression member. If you have tension force alone, if you have compression force alone, if you have bending moment alone. But right now, your frame, maybe your frame column, we have bending moment diagram. At the same time, we have normal force diagram. That's right? So, go back to this diagram. Yes, my frame under the effect of load, dead, live, wind, or whatever. At the same time, your column under the effect of compression force and bending moment. your beam of your frame under the effect of normal force, at the same time we have bending moment. So what do you think? This member is still called column, but we have moment. It's still called beam. This member, is it called beam? But we have normal force, compression. So it's called column. We have something in you called beam column design. So design of beam column. I'm sorry, what you mean? Is it beam or column? Two. I cannot call it beam because we don't have bending moment only. I cannot call it column because we don't have axial force only. We have both of them. So we can call this member beam column. You got it? So we have combination of internal forces on the same member. What will happen? So while main structure member can be treated as axially loaded column only, and beams under the effect of bending. So if your member under compression, we can call it under compression only, axial force compression only. We can call it column, that's fine. If your member under the effect of bending moment only, you can call it beams. But sometimes your member under the effect of both of them, most beams and columns are subjected to some degrees of both bending and axial load. Then your member can be called beam column member. If you would like to design, we would like to design beam column member. What will happen? We will do combination between this case and this case. How? We did a little bit in Berlin, design of Berlin. Anybody remember what we have in Berlin? Do you remember?
What's happening?
We have combination. Your cross section of Berlin was inclined, but your force is a vertical force. So we get component of this force in the same axis of your Berlin and this axis. So we have two components, like this one and this one. One of them will do moment about x, and the other one will do moment about y. And do you remember what was the interaction combination equation? M ultimate x divided phi mn x plus m ultimate y divided 0.5 phi mn y smaller than or equal what? 1. And we said, hey, to get your design more economic, this value must be very close to 1, maybe 0.9 to 0.99. That will be more economic. We will see this combination or this interaction equation one more time, but we will add one more term. The relationship between required and the available strengths may be expressed as the required strengths must divide available strengths must be smaller than or equal 1. Did we learn this equation before? Did you see it before? Did you? Yeah, believe me. P ultimate must be smaller than or equal phi F critical area gross. That's right. M ultimate must be smaller than or equal phi M normal. I'm sorry, M nominal moment. So what's your left side? Your left side is the required strengths, the actual strengths, the actual load, the actual moment on your frame or on your structure. What about the right side? The right side is your design strengths or your available strengths. What will happen if you divide this term by itself, phi F critical area gross? and this term by the same term, phi F critical area gross. What is the final? The final here will be your P ultimate divided by phi F critical area gross smaller than or equal 1. So the required strength we need to design according to this load. Divided by the available design strengths must be smaller than or equal 1. So required strengths from structure analysis, available strengths from your design must be smaller than or equal 1. This is your design philosophy, but in different way. Anyway, for compression member, P ultimate must be smaller than or equal design compressive strength. So if you get this value to the other side will be a dominator, then P ultimate design phi Bn smaller than or equal 1 for compression member. For bending moment, your M ultimate must be smaller than or equal your design bending strength. Get this term to the other side will be a dominator. So M ultimate divided by phi Mn will be smaller than or equal 1. What will happen if you have compression and you have bending at the same time? What will happen? Nothing in you, just this equation, ultimate load from structure analysis divided by your compressive design strength plus this equation, your factor bending moment from structural analysis divided by your design bending strength, both of them must be smaller than or equal 1. This is equation called interaction equation for a combination between axial force and bending moment.
So it's even safer than,
What?
it has to be way safer, right? Because you can't have like 0.75 for one for the bending and then like 0.5, because then that would mean.
Yeah. If you have here 0.75, 0.5, you are unsafe. You need to increase your cross section. But at the end, the summation, I don't care what is this value and what is this value. My concern is the total